Hey everyone. In this video, we're going to start to see how we can actually start modeling mechanical energies more explicitly. Like I said in the last video, one of the nice things about mechanical energy is that all of the stuff that we've learned for internal energies works just as well for mechanical energies. We can draw energy interaction diagrams just like we would with thermal energy and bond energy. Let's look at a really simple example, the case of the falling object. This person is holding this ball some distance above the floor. When they drop it, we know exactly what's going to happen. The ball is going to fall. But we also now know why it falls. When the person holds it in the air, the ball has gravitational potential energy, energy that it has because it is above the ground. When we drop it, that energy is converted into kinetic energy as the ball falls. Its gravitational potential energy decreases because its distance above the ground is decreasing. Similarly, its speed is increasing because its kinetic energy is increasing. Let's really quick draw an energy interaction diagram for this. We've identified two kinds of energy that matter, the gravitational potential energy and the kinetic energy. But let's start by writing out what our physical system is. Now, you might be tempted to say your physical system is just the ball. It's the only thing that we care about. But this is not quite true, and here's why. In order for an object to have gravitational potential energy, it must have something that's causing the gravity, right? An object out in the middle of space with nothing around it doesn't have gravitational potential energy because there's nothing pulling on it with gravity. So what's pulling on the ball that gives it gravitational potential energy? The answer is actually the Earth. The Earth has mass, and anything with mass generates gravity. So our physical system is actually the ball and the Earth together. Again, if the Earth wasn't there, the ball could not have gravitational potential energy. Now that we've figured that out, let's try to draw bubbles. As we know, there's only two kinds of energy here, the gravitational potential energy and the kinetic energy. The gravitational potential energy is actually the gravitational potential energy of the ball and the Earth together. We represent gravitational potential energy like this. The PE stands for potential energy, and the G stands for gravity. What is the gravitational potential energy of the ball doing as it falls? By this I mean, is it going up or is it going down? Well, if you've thought about what gravitational potential energy is, you can probably answer this question. The gravitational potential energy of the object is going down. The lower the height, the closer it gets to the floor, the less gravitational potential energy it has. How do we know that its gravitational potential energy is going down? Well, I just said it. It's because the height of the ball is decreasing. Its distance from the floor is going down. So we know that our gravitational potential energy is decreasing because the height of the object is decreasing. What about the kinetic energy, though? The kinetic energy is the energy that the ball has due to its speed. Unlike with the gravitational potential energy, the ball doesn't need the Earth in order to have kinetic energy. It just has kinetic energy because it's moving. We represent kinetic energy with a big KE, like this. What's happening to the kinetic energy as the ball falls? Well, think about how much kinetic energy the ball has when it's dropped. Initially, the person is holding the ball in the air and the ball is not moving. Kinetic energy is energy that an object has because it's moving, so it probably doesn't surprise you that an object that is not moving has zero kinetic energy. As the ball falls, it starts to move. Its kinetic energy is increasing because its speed is no longer zero. And in fact, the farther it falls and the more it loses its gravitational potential energy, the more its kinetic energy increases and the faster it moves. So kinetic energy goes up. We know kinetic energy is going up because the speed of the ball is increasing. It's not moving initially, and then it starts moving. We represent speed in physics with a v. I know that this maybe doesn't make sense right now. It will at some point, but this is the letter that we're going to use. The last thing we have to ask is whether this is an open system or a closed system. This turns out to be a little bit tricky for these kinds of cases. After all, we're now including the entire Earth in our system, so it's hard to say whether this is open or closed. But for now, we are just going to call it a closed system. The last thing we want to try to do is write an equation that describes what's going on here. As always, we start with our basic energy equation. The change in the total energy of the system is equal to the heat plus the work that goes into or out of the system. But this is a closed system, so we already know what the heat and the work are. They're just equal to 0 because no energy is allowed to enter or leave the system. Now, we want to expand our delta E total into the individual kinds of energies that matter. We already know how to do this. We just have to look at our bubbles. We have two bubbles, so we're going to have two terms in the equation. The first term is just the gravitational potential energy of the ball, delta P E G. And our second piece is just the change in the kinetic energy of the ball, delta KE. This is all equal to 0. All this equation says is that as the ball falls, the potential energy, the gravitational potential energy of the object, is just being converted into kinetic energy. Now, we will see how to write this out mathematically next week. For now, the key takeaway is to remember that mechanical energies can be modeled in the exact same way as internal energies. One of the really nice things about mechanical energies is we tend to have good intuition about them already. You knew off the top of your head that if you drop a ball, or anything really, it's just going to fall. I encourage you to use those intuitions to help you to solve problems. But just remember that at the end of the day, you still have to be able to write down an energy interaction diagram and an equation. These equations, just like with internal energies, will allow us to make specific predictions about how the world will behave in the future. Enjoy the weekend. I'll see you next time.